Hello, everybody. Good morning or good afternoon, depending on your current time zone. I am very pleased to present our work from the historical building of Charles University. Our topic today is the efficient representation of fluorescent spectra. Hope you enjoy. Fluorescent materials are quite common. They have a particular behavior. They radiate received wavelengths to other parts of the spectrum. This means the reflected color is not a shade of the color used to lit the material. On this time lapse, you can see the post-it and the glass reflected received light with a different color than the one used to lit them. The bispectral behavior of fluorescence, we can use a reradiation matrix. Those matrices represent, for a given radiating wavelength, what is the reflected spectrum. In this basic example, we could measure for each of the frame lit by the monochromatic light the reflected spectrum of one of the post-its. We end up with this radiation matrix. Now, how do we handle such phenomenon in path tracing? Just let me show a simple example of standard path tracer computing the interreflection between objects in the scene. Each path in the space is bounces through the scene. And in each intersection, we are going to calculate the BRDF. Now, if one of the objects in the scene is fluorescent, the wavelength carried by this ray will be shifted after the reflection. The color of the fluorescent material is shifting to a more saturated color. To present this behavior is the radiation matrix we shown before. In reality, the radiation matrix is a set of measured data. But let's just simplify it as a matrix with numerical numbers. This matrix is huge since it needs to cover the range of visible wavelengths. Each numerical value here means the probability that the wavelength is going to be jumped to another one. Now there comes a problem when used in the radiation matrix. The rendering system is fine when there is only one type of fluorescent material. But what if we have many types of fluorescence in the scene? Even worse, what if our artists want to have a texture with fluorescence, where each pixel contains a different radiation matrix? There will be endless matrices in your memory, thus making the fluorescence not be usable in practice. Our work is trying to solve this problem. Let's review some previous work in the world of fluorescence. Mojic and colleagues proposed in 2018 a method to render fluorescence with hero wavelength spectral sampling and a tracking scheme to render fluorescent media. As we shown before, fluorescence gives us the more saturated color. Young and colleagues use these characteristics to enlarge the color gamut when uplifting. It means they are providing bispectral textures. This requires a large amount of memory because it requires to use radiation matrices for each pixel. With our method, we aim to significantly reduce the memory footprint of such bispectral data. In our method, we are using Gaussian mixture models. These type of representations are widely used in computer graphics. For instance, Voba and colleagues use the Gaussian mixture to accelerate light transport, whereas Hohorst and colleagues use it for efficient BRDF importance sampling. Gaussian mixture models provide fast evaluation, compact representation, and importance sampling. In our method, we show Gaussian mixture model is also well suited to efficiently represent fluorescence reflectance, while allowing compression and importance sampling. Let's dive into our proposed method for solving this matter. Our pipeline starts with a tabulated radiation data. In previous work, it is fully stored in memory and used directly in the wavelength sampling. We are now focusing on fitting of this radiation cluster. Notice the diagonal is removed here because it is a place where no fluorescent event will occur. Before we fit the data, we filter the high frequency noise under the certain threshold. And then we can perform the expectation maximization on it. But before we perform the EM, we need some modification. Each of our data has one weight. If you divide each element by the integral of the matrix, each will represent as a tabulated PDF. The first option of the modification is to duplicate this data by a large number, and the resulting dataset still has the same portion of weight. Then you can perform the standard EM algorithm on it. But this leads to a huge observation set. Another option is to use a weighted EM, where the preceding training parameters in the algorithm is balanced by the weighting factor. In our pipeline, we will consist with the weighted one. After the fitting step, we have a set of Gaussian mixture parameters that we load into the render. Those parameters will be cut-shot and used for fluorescent events. There are in total 7 elements plus a weighting factor. The first set of parameters is the GMM, which uses 56 bytes for each Gaussian. We experimented that even with small number of Gaussians, it can already has a good performance. The second set of parameters is a weighting factor we use to reconstruct the radiation attenuation. To going from the Gaussian mixture to fluorescent albedo, we will need to apply this weighting factor, and it takes 8 bytes for each fluorescent material. So if we record the full representation of the tabulated radiation, it needs 9,000 bytes for cache in such radiation. This radiation is sampled at 10 nanometer. Let's have a simple illustration on how the wavelength shift is being done on a 2D matrix. If we encounter any fluorescence material, there will be 2 possibilities. The ray is reflected with the same wavelength as the radiating ray. This means there is no fluorescence. In this case, we will sample the diagonal. Or the ray is re-radiated to a different wavelength. This means there is a fluorescent event happening. In this case, we import and sample the radiation. We do this by the conditional Gaussian mixture distribution. We will not dive into the mathematics here, but just to give you some insights on the conditional Gaussian mixture, it's just a slice sampling you can perform on the 2D radiation. By giving the input wavelength, it gives you what is the distribution of your output wavelength. And depending on the sampling path, you can either outshift or inshift. And here is an example of the conditional PDF compared to the yellow fluorescent datasets shown in purple curve. The green curve is the expected distribution of the re-emission wavelengths when the material is irradiated at 480 nanometer. Notice the measurement noise present in the original data lowers the highest value of the PDF after normalization. Now let's see some results. Results we are showing is a fluorescent sphere using 3 different datasets: green, pink, and yellow. Now we show you the rendering of the same datasets after being compressed using our method. As you can see, it is hard to see any visual difference. Now, even with a very challenging scene, we get convincing results. Indeed, here each scene is lit by near UV light. This means most of the contribution comes from the fluorescent effect, which is fully approximated by the Gaussian mixture in our method. Even with such challenging case, we barely see the difference. Our method not only provides convincing result, but also drastically reduces the memory footprint. On the left, the raw measurements are used to render the scene. It requires 27 kilobytes, while on the right, we use our method to represent the fluorescence data. Our method uses less than 2% of the memory required by the raw radiation. The memory difference is even larger with fluorescent texture. This texture is 32 by 32. Among those pixels, we have 255 fluorescent ones. The raw representation needs 258 megabytes for both spectral and bispectral pixels, while our methods only require 4 megabytes for this texture. If you increase the resolution of the texture, the ratio is getting even bigger. This means our method makes the usage of bispectral texture practical. Finally, we will address some feature work. So, in conclusion, our method is memory efficient and allows fast evolution and important sampling. It also provides convincing results even with challenging illumination. However, in future work, we would like to explore different families of functions, possibly with positive skewness to have better representation for our original data. Also, we describe in the paper 2 strategies to improve visual appearance by rescaling the GMM. Further work will be done in this direction. We hope this presentation will encourage our community to provide new measurement data for fluorescent materials. As a matter of fact, we were limited to a very restricted sample set of measurements to evaluate this work. Having access to a larger set of measurements would benefit future works for efficient representation of bispectral materials. Thank you very much for your attention. We made the implementation of this paper open sourced. You can find it following this link here. We rely on art for all of the rendering results. If you have any questions, we will be very pleased to answer.